So we're going to start our next section, which is 15.1, and it's about vector fields. So we're going to start with the definition. A vector field over a plane region R. So remember, this is a region in the xy plane, is a function, capital F, that assigns a vector, which will be f of xy, to each point in R. Now you can also define a vector field over a three-dimensional region. So we'll say a vector field over a solid region Q in space is a function, still capital F, that assigns a vector to each point in space. So we've actually already seen examples of vector fields before. Can you think of those examples we've already seen? Well, in particular, what we talked about previously is the gradient. So the gradient is an example of a vector field. So that's our previous example, was the gradient. Let's just remind ourselves, right? Look at an example. Let's say my function f of xy is x squared y plus 3xy cubed. Remember that the gradient is written as the partial derivative with respect to x times I plus the partial derivative with respect to y of j. So here, if I look at my partial derivative with respect to x, this will be 2xy plus 3y cubed. The partial derivative with respect to y would be x squared plus 9xy squared j. And this is a vector field. I plug in a point and it outputs a vector. There are a lot more physical examples of vector fields. So the first one being velocity fields. The second one, gravitational fields. And then third, I'd consider electric force fields. These are all examples of vector fields. To each point in space, you have a vector that corresponds to these objects: velocity, gravitation, and electric force.